Hello everybody, I'd like to do our second video on group homomorphisms. So if you remember, a homomorphism between two groups, G and G bar, is a function phi mapping elements in G to G bar, satisfying the following property. If you take any two elements, A and B, in G, and then you combine them in G, and then you map them over into G bar by the map phi, then that's the same thing as taking A, mapping it by phi into the group G bar, taking B, mapping it into the group G bar by phi, and then taking those two elements phi of A and phi of B, and then combining them together in the group G bar. So here, this multiplication is happening in the group G, whereas this multiplication here is happening in the group G bar. So far in this class, we've studied isomorphisms a lot, and isomorphisms are just one example of homomorphisms. In an isomorphism, groups G and G bar have to be the same size, and furthermore, phi needs to be a bijection. But for a homomorphism, groups G and G bar can be different sizes, or even if they are the same size, the map phi doesn't need to be an bijection. Okay, an important concept that I'll come with today is the kernel. So the kernel of a homomorphism phi is all of the things that get mapped to the identity. So the kernel is all of the group elements in G that get mapped to the identity in G bar. So for example, last time we saw this homomorphism from Z4 to Z2. It mapped 0 and 2 to 0, and it mapped 1 and 3 to 1. The kernel was all things that mapped to 0, so the kernel was just 0 and 2. Okay. We'll find out today that the kernel is not only a subset, but it's also a subgroup. And indeed, the set containing 0 and 2 is a subgroup of Z mod 4Z. All right. So that's a kernel. The kernel of a homomorphism phi from G to G bar is all elements in G that under this map phi get mapped to the identity of G bar. Alrighty. So let's get to the new content today. First, I want to describe a homomorphism that's slightly trickier than the homomorphisms in the earlier parts of my notes. So I'll use some language that maybe not all of you are super comfortable with, but that's okay. It's good to get exposed to things. So GL2R has come up before in this class. We haven't worked with it a lot, but it's the group of all 2 by 2 invertible matrices. So the 2 means 2 by 2 matrices, and the R means that the entries of those matrices are just real numbers. Invertible is just the same thing as having a non-zero determinant. Okay, so a matrix is invertible if and only if it has a non-zero determinant. The homomorphism that I've written down here is the homomorphism phi going from all such 2 by 2 invertible matrices to the non-zero reals equipped with multiplication. Okay, so if those are both groups and phi is mapping between them, phi sends a matrix A to its determinant. Okay. So first of all, notice that since A is invertible, it has a non-zero determinant. So I am indeed mapping to this collection of non-zero reals. You'll remember that superscript star means the non-zero reals. And furthermore, this is a group homomorphism. If you've taken linear algebra before, you'll recognize this property that the determinant of matrix A times matrix B happens to be equal to the determinant of A times the determinant of B. Okay, this is really, you should be thinking of this equation as the equation phi of little a little b is equal to phi of little a combined with phi of little b. Okay, here little a and little b just happen to be matrices that I've called capital A and capital B, and my function phi just happens to be the determinant, right? That's how I'm getting from a matrix to a non-zero real number. I'm taking its determinant. Yeah, so if you've taken linear algebra, you might have seen this formula before, and you should recognize that as, oh, that's really the formula showing that this map is a group homomorphism. What's the kernel of this map? So the identity in the non-zero reals under multiplication is 1. 1 is the multiplicative identity. So the kernel is the collection of all matrices that map to 1, i.e. the matrices with determinant 1. Okay. Some properties about homomorphisms. Let phi be a group homomorphism from G to G bar, and let G just be an element in our group. Okay, so we have two properties. The first property is that the identity in G gets mapped under this homomorphism to the identity in G bar. I can give you a quick proof of that. Okay, it's right here. Let me zoom in on this. So why does the identity in G under a homomorphism have to get mapped to the identity under G bar? Okay, well, one thing that I know is that if I choose little a and little b to be the identity, I still have this group structure preservation property. So here I have, this is phi of a combined with b, when both a and b are the identity. And that I know is phi of a combined with phi of b. Okay, so this first equality is just the fact that phi is a homomorphism. Then the identity times the identity in G is just the identity. So that gives me this next equality here. And then this equality is just because I'm now in G bar, and the identity in G bar multiplying by it doesn't change anything. So I have this element phi of the identity in G. That's an element in G bar. So if I multiply it by the identity in G bar, it doesn't change it. That's this last equality. Okay, it seems a little roundabout. What am I doing here? What am I going for? But the point is, now I can do cancellation. So now I can cancel this guy with this guy. So I'm doing left cancellation. And I get that phi of the identity in G is equal to the identity in G bar. So I apply cancellation to get that phi, my homomorphism, is mapping the identity in G to the identity in G bar. Do you like that? That's sort of a cute proof. It's one of those proofs that might be hard to come up with yourself, but once you see it, you can sort of understand it and then try to understand it and commit it to memory. Okay, and the second property is if G is any element, little g. So if little g is any element, then phi of G combined with itself n times is equal to phi of G combined with itself n times. Okay, so when I combine G with itself n times, I'm doing that in the group capital G. When I combine phi of G with itself n times, I'm of course doing that in the group G bar, capital G bar. I can explain this a little bit. So let me just do examples for small values of n. All right. So for n equals 2, what this is saying is that phi of g squared, well, let's just do it. That's phi of g combined with g. Since phi is a homomorphism, this is just phi of g combined with phi of g. So that's since phi is a homomorphism. All right, and then another name for what I have on the right is just phi of g squared. How does this look for n equals 3? For n equals, whoops, sorry. How does this look for n equals 3? I have v of g cubed. Well, that's phi of, one way I could write g cubed is g squared times g. Okay? And now, since phi is a homomorphism, this is phi of g squared times phi of g. Phi of g squared, we just saw what that was. That's phi of g quantity squared, right? That's this, that's this equality up above, right there. And I still have a phi of g along for the ride. And what is this that I have here? This is 3 copies of phi of g. This is phi of g cubed. All right, so you could do something similar to see for n equals 4 that phi of g to the 4th power is actually phi of g to the 4th power. And in general, what we get is phi of g to the nth power is phi of g to the nth power. You could prove that using induction on n, but we won't. Alrighty. Let's keep going. So our next theorem is theorem 10.2, and it says the following. Let phi be a group homomorphism if H is a subgroup of G, and if K bar is a subgroup of G bar, then we're going to see some things about the image of H under phi and the preimage of K bar. All right, so if H is a subgroup of G, then phi maps that to a subgroup of G bar. That's this first bullet. The second bullet says properties of the subgroup are preserved. If H is cyclic or abelian or normal, then phi of H is not only a subgroup, it's also a cyclic or abelian or normal subgroup. Okay, so properties that H have, such as being cyclic or abelian or normal, are inherited by phi of H. The third bullet says if K bar is a subgroup, then its preimage, if K bar is a subgroup of G bar, then its preimage, phi inverse of K bar, is a subgroup of G. Okay, so the preimage of K bar, what's the preimage of K bar? The preimage of K bar is just all those elements in G that map to K bar under phi. Only one property of note is preserved under preimages of subgroups. So if K bar is a normal subgroup of G bar, then its preimage is a normal subgroup of G. Okay. So in summary, this theorem is saying that subgroups of G map under a homomorphism to subgroups of G bar. Properties of those subgroups, like being cyclic, abelian, or normal, get mapped over to the resulting subgroup in G bar. And vice versa, if you have a subgroup of G bar, its preimage is a subgroup in G. And if that subgroup of G bar is normal in G bar, then its preimage is normal in G. The most important example of this is as following. The identity in G bar is clearly a subgroup of G bar. It's just, you know, the simplest, most trivial subgroup you could think of. All right. And so theorem 10.2 says its preimage, the preimage of the identity, in other words, the things that map to the identity in G bar, in other words, the kernel of phi. Okay. So the preimage of the identity is just the kernel. This preimage, a preimage of a subgroup, is a subgroup. So the kernel is always a subgroup. This was our example here. We asked what mapped to the identity in Z mod 2Z. And it was these two elements, 0 and 2. That was the kernel. And we know that the preimage of the identity, or the kernel, is always a subgroup of G. Okay, so we now know that kernels are subgroups. The next important fact is that kernels are always normal subgroups. Just because this trivial group consisting only of the identity in G bar is always normal, but we know preimages of normal subgroups are normal. So we're going to see that kernels are always normal. Okay, this is written out in detail here. Moreover, note that the identity in G is a normal subgroup. Sorry, note that the identity of G bar is a normal subgroup of G bar. Here's the proof. For any element A in G bar, the left coset A times the identity is just A, and that's the same as the right coset A times the identity. Okay, so that's our proof that the trivial group consisting only of the identity in G bar is a normal subgroup of G bar. But you'll remember this theorem said that the preimage of a normal subgroup is a normal subgroup. Okay? So hence this theorem above says that the preimage of the identity, or in other words, the kernel of phi, is a normal subgroup of the group. Okay, let me write that a little bit more clearly. The preimage of the identity in G bar is just another name for the kernel of this homomorphism phi. So in some sense, kernels and normal subgroups are very tied together. Right now, you can think of a kernel of a homomorphism as an example of a normal subgroup. But as we'll see later, every normal subgroup can also be seen as a kernel. Okay? So in some senses, kernels and normal subgroups are the same things. Right now, I've shown you that a kernel is a normal subgroup, but furthermore, it's true that every normal subgroup can be expressed as a kernel. Let's do some examples talking about kernels and the fact that they're normal subgroups. Okay, so let n be an integer. Alrighty. Let n be an integer, and we'll have this homomorphism phi from the integers to z mod nz. And we just map the integer j to j mod n. Okay, this is a homomorphism, and its kernel is all things divisible by n. So 0, n, 2n, 3n, n, negative 2n. I guess that's a very small typo there. I want a negative n here. Okay. So its kernel is just all the numbers divisible by n. Another name for that is nz, or the subgroup generated by n. All right. Now, since kernels are always normal, we know that nz, this kernel, the integers divisible by n, is a normal subgroup of the integers. And that's why we can do this quotient group. You can only do quotient groups when you know that the subgroup is normal. And we have that here. We've exhibited nz as a kernel. And so we know that nz is normal. And that's sort of why we're allowed to take this quotient in the first place. Okay, here's one more example. I can define a homomorphism phi from the symmetric group to the z mod 2z by sending a permutation sigma to 0 if it's in the alternating group, and to 1 if it's not in the alternating group. Okay, so you can check that this is a homomorphism. Checking that relies on checking that an even permutation times an even permutation is even, an even permutation times an odd permutation is odd, and an odd permutation times an odd permutation is even. Okay, but what's the kernel of this homomorphism? The kernel of this homomorphism is pretty clear. The kernel of this homomorphism is just all the things mapping to the identity in z mod 2z, i.e. all the things mapping to 0. Well, that's just the alternating group. Okay? So I sort of told you previously that the alternating group is always a normal subgroup of the symmetric group. Here's a different way of thinking about that. We found a group homomorphism where the alternating group is the kernel of that homomorphism. And since kernels are always normal, so is the alternating group. It's a normal subgroup of the symmetric group. All right, thanks so much for your attention. Next time we'll talk about the first isomorphism theorem, which is also closely related to normal subgroups and kernels. Thanks.